Okay, so for conceptual questions number one, accompanying figure show two situations, an electric field vector and induced magnetic field line B, which statement is correct. So to answer these questions, let's consider the induced magnetic field line in the figure A, which was the counterclockwise directions, and according to the right thumb rule, uh, the the delta E that should happen like the electric field vector that should be is in the upward directions according to the right thumb rule, the delta E. Therefore, the electric field vector E should be decreasing in the same way as in the figure B. The clockwise induced magnetic field line B implies that the delta E was in the downward directions and result in the decreasing of the electric field vector E in both figures. So the answer is 2. Thank you.
Hello teacher King. For the second conceptual question is question 3. Figure gives the variation of an electric field that perpendicular to a circular area of 2 meters square during the period shown. And it asks about the greatest displacement through the area. Firstly, for the displacement current is equal to epsilon 0 multiplied by the flux E by dt, and the flux E by dt is equal to A dE by dt. So if we want to find the greatest displacement, we need to find the highest dE by dt, which is the highest slope in this graph. And in this graph, it's divided into 4 parts. For the first part, the slope of the first part is clearly seen that is equal to 0. For the second part, is equal to delta y divided by delta x, which is 2 minus 6 divided by 6 minus 2, which is minus 1 in the unit of Newton per Coulomb microsecond. For the third part, the slope is equal to 4 minus 2 divided by 7 minus 6, which is 2 Newton per Coulomb microsecond. And the last part, the slope, which is delta y divided by delta x, is equal to 0 minus 4 divided by 12 minus 7, which is 0.8 Newton per Coulomb microsecond. So we can find the highest slope, which is the third part, is equal to 2, and we will find the displacement currents, which is epsilon 0 A multiplied by 2 Newton per Coulomb microsecond, and the epsilon 0 is equal to 8.854 multiplied by 10 over minus 12 in the unit of Coulomb square divided by Newton meter square. For area is equal to 2.0 meters square. And the last one, which is dE by dt is equal to 2 Newton per Coulomb microsecond. So we can find the displacement current, which is equal to 3.5 multiplied by 10 over minus 5 Coulomb per second, which is 3.5 multiplied by 10 over minus 5 ampere.
Okay, so for the question number 4, the voltage across a parallel plate capacitor with the area A and the separation D, the V vary with time as V equals to AT squared. A is constant, and the equation is to find the displacement current between the plates. So from the Maxwell equation, we can have that displacement current is ID equal to epsilon 0 and the changing of flux over time. We have that electric flux equal to E dot A. We substitute that in the equation and get ID equals to epsilon 0 times. We can pull A out from the differentiation as it was a constant, and we differentiate the electric field over time. We also get that E is equal to V divided by the separation. Substitute that and get epsilon 0, pull the separation out, and differentiate the voltage over time. And from the questions, we have that V is AT squared. So substitute that into the equation. Dip AT squared over T. And let's dip together and get 2AT. And lastly, arrange it in more beautiful posture. You get 2 epsilon 0 A area time divided by the separation. This is the answer of the question number 4. Thank you ขอบคุณครับ
For question 5 in calculation, 0.2 ampere current is charging an air parallel plate capacitor whose circular plate is 10.0 cm in radius if the plate separation is 4.00 mm. For the first question is asked about the time rate of increase of electric field between the plate, which is asked about dE by dt. So from Q equal to CV, C is equal to epsilon 0 A divided by D and V is equal to ED. We can get that Q is equal to epsilon 0 AE. And if we differentiate d by dt in both sides, for the left side, d by dt, so it's equal to dq by dt, and for the right side is epsilon 0 a dE by dt. So we can get dE by dt by dq divided by dt divided by epsilon 0 a, and dq by dt is I. So its dE by dt is equal to I epsilon 0 a. For I is equal to 0.2 ampere, and epsilon 0 is 8.85 multiplied 10 over minus 12, and A is pi r squared, which R is 10 centimeter square. So we can get dE by dt equal to 7.19 multiplied 10 over 11 Newton per Coulomb second. Question B is asked about the magnetic field between the plate at the distance 5.00 cm from the center. We can find the magnetic field from the Ampere law with Maxwell modification, which is integrate B dl equal to mu 0 I plus epsilon 0 d flux E by dt. And for the left side is equal to B multiplied 2 pi r. And for the right side, we consider only between the capacitors, so there is no conduction current in this, so I is equal to 0. And the right side is equal to mu 0 epsilon 0 d flux E by dt, which equal to B multiplied 2 pi r equal to mu 0 epsilon 0 a dE by dt. And we can get that B is equal to mu 0 epsilon 0 a dE by dt divided by 2 pi r. So from mu 0 is equal to 4 pi multiplied 10 over minus 7. Epsilon 0 is equal to 8.85 multiplied 10 over minus 12. And the area is equal to pi r squared. And dE by dt from the last question is 7.19 multiply 10 over 11 divided by 2 pi r. And we can get that is 4 pi multiply 10 over minus 7 multiply 8.85 multiply 10 over minus 12 multiply r, which is 5 multiply 10 over minus 2 and multiply 7.19 multiply 10 over 11 and divided by 2 is equal to 2.0 multiply 10 over minus 7t.
Okay, let's move on to the number 6. It said the time varying electric field E is shown in figure 4. So it's this picture. And the vertical axis scale is set by ES equal to 6.0 times 10 to the power of the 5th. So we can label this one is 6, this one is 4 and 2. And for horizontal axis, TS equal to 12. And so it should be 10, 8, 6, 4, and 2. It said calculate the magnitude, right, of displacement current through 1.6 meter square area that perpendicular to the field during each interval A, B, and C. Okay, first thing you need to know is the formula of displacement current, right? It is ID equal to epsilon naught the flux by dt. But flux is E times A, right? So it should be epsilon naught dEA by dt. But A is constant at 1.6 meter square, right? So that we can rewrite it here, 0 naught epsilon naught times A and times dE by dt. But let's look at the graph. What is dE by dt? It is the slope of the graph, right? So it is the slope. We can shaded it here. So now we are ready to move on to those intervals. First, IDA. And we want to find only magnitude, right? So that we put absolute here. Equal to epsilon naught is what? Epsilon naught is the constant at 8.854 times 10 to the power of minus 12 Coulomb square per Newton meter square. And A is 1.6 meter square, right? and then the slope is 4 minus 6 over 4 minus 0, so it's minus 2 times 10 to the power of the fifth Newton per Coulomb, right? And for time is 4 but millisec, so it will be 10 minus 6 second, so that we can cancel the unit here, c and m square and n, so it will be Coulomb per second. As we know, it is ampere, so the result is minus 0.71 ampere, but we consider only the magnitude, so we put absolute, it will become 0.71 ampere. Done. Now for interval B, IDB. Okay, let's look at the graph. The slope here is equal to 0, so that 0 times anything will be 0, so we can answer 0 ampere easily. Okay, the last one, IDC. Here equal to absolute 8.854 times 10 to the power of minus 12 Coulomb square per Newton meter square times 1.6 meter square and times the slope, right? It will be 0 minus 4 over 12 minus 10. It is minus 4 times 10 to the power of the fifth Newton per 2 times 10 power of minus 6. And as you see, it is 4 times much than the result from interval A, so that it is minus 2.8 ampere and become 2.8 ampere. And this is the answer of this question. Yeah.